Hi. So we're being late a bit because of the traffic. It's a big problem. So without further ado, let's get started. Um, Before we start, any question? Any question before we start? If no, then today the goal is we will finish the hypothesis testing, and then first day with a quiz on the hypothesis testing. So if we finish today, then it will be a quiz. I think we're able to finish it, but let's see what can be done. I think we're able to do it. Next class will be quiz, and then we will also start from ANOVA. Okay. And any question? And if there's no question, then we get started. Okay, so hypothesis testing. So just to basically recall quickly what we have. What we have is the following, right? Is hypothesis testing, right? We have divided this topic into two parts, right? One is one sample, right? The other is two sample. Okay. And for one sample, basically we just learn two things, whether we are looking at the mean or look at the proportion, right? And for the proportion, we always use z-test, right? And we use z-test when we know sigma square. When we don't know, we do t-test, right? Unknown sigma square, right? And then depend on the alternative, then you put the rejection region on one way or the other, right? Depends on what you set the alternative to be. And the two sample tests, here we focus on unknown sigma square, so we use t-test. Maybe I erase a little bit. Here we also have two things, mean and variance. Okay. And we focus on the case where we have unknown sigma square. So we always focus on t-test here. And there are three different t-tests we focus on, right? Because two sample, then we have equal sigma square, unequal sigma square. Another is a paired t-test, okay? And the variance, you have f-test, okay? This question here, let's see. Sample proportion, yes, with z-test, because the question is for proportion, Oh, yes. I think we also have one thing. With proportion, right? Yes, we also have z-test. Yes. So the answer to the question, the difference of portion, and then that will be a z-test too. Okay, let's see if any question. So the goal of today is to, I think, to cover the last three tests. So goal of today will be covering a pair t-test, proportion c-test, and variance f-test. So that is the goal today, to cover these three tests. Any question? If there's no question, then we will get going. Okay, so let's get started. Okay, so very quickly we cover the equal and equal variance again quickly, and then we'll do the pair. And then I think I missed one thing here. So so first, to recall, a little bit complicated, so that's why we revise again. Okay, so here we have two distribution of independent, right? We have asking, so basically we have, we're looking at this, right? We're sample. So basically we have, maybe I use a whiteboard. So you have let's repeat, your population 1, and there's another population 2, okay? And you draw a sample, okay? You got sample 1, okay? Another sample, you have sample 2, okay? From sample 1, you can calculate mean x bar 1 as 1, okay? And x bar 2 as 2, okay? So no, we don't have quiz today. We'll quiz on Thursday. We'll finish everything, and then we'll quiz on Thursday. So here we are looking at this element, okay? And this element would have normal distribution with x1 bar minus, sorry, with mu1 minus mu2, and mu1 and mu2 are the parameter of the population, okay? And we have sigmas, they have the equal proportion, right? So they have same sigma, okay? So will be sigma over n1 plus sigma over n2, okay? And so I should be saying this is n1 of them, n2 of them, okay? So we can use, if we know sigma, then we can use normal, right, to do the job. So usually we don't know sigma, so we have used the t, right? So this, of course, you know the sigma, then we can use the same method because this is just normal, right? But the fact that we don't know, then we need to use other way around, right? We'll use this idea, all right? And minus mu1 minus mu2, okay, over square root, okay, of this s square 1 over n1, 1 over n2, right? It will be a t distribution with n1 plus n2 minus 2. And this s is given by a complicated object, which is this S or SP to be a following the notation will be N1 minus 1, N1 plus N2 minus 2, S1 square plus N2 minus 1, N1 plus N2 minus 2, S2 square is a weighted average of S1, S2. And this is a best estimate of S pooled variance, right? Sample variance, and this will be a T. Okay, we can do this for the hypothesis testing. Is that okay for this one? Any question? Okay, so this is what we have. Okay, so another thing we have is an unequal variance, right? So this is the second thing. We have population 1. We have mu1. Now we have sigmas 1 square. Okay, so we have population 2 will be mu2 sigma 2 square. Okay, again we can draw a sample of N1 sample. Okay, and this sample will give us x1 bar, S1 square sample variance, and we can redraw an N2 sample. Okay, and then what we have is x2 bar, S2 square. Okay, so this is sample variance, sample mean. Okay, and by central limit theorem, or then you know this is going to be a normal distribution, right? With mean mu1 minus mu2 and S1 square over sigma 1 square over N1 plus sigma 2 square over N2. Again, if you know N1, N2, we can just do very simple hypothesis testing, right? Just you know N, but you don't know, then use T, right? So basically what you have is this guy, and then you replace sigma 1 by S1. Sigma 2 by S2. Okay, and when you replace this, then you will become a T distribution. And the tricky part is what's this guy? Okay, and this guy turned out to be a very complicated expression. I'm not going to write here, but turn out this is of course one of the most difficult things. But you look at the formula, it's not complicated except this complicated object. But this object is not too, as we can see, that's not too much far away from N1 plus N2 minus 2. But it sometimes is different, but it should not be too much different from that. Then that's how we are doing the inference and estimation. Is that okay? This is thing we covered last class. Would there be Excel formula for the calculation? Well, Excel has a T distribution, right? So you can just directly do it. Did I answer a question? So if we have time to talk about that, but there's no exact formula for that. We'll talk about that. I mean, if you have time. If not, then we'll talk about tomorrow after the quiz. But I think everything is pretty clear. Is that okay for the moment? I hope. Okay, is that okay? Then we go to stop the review, and then we go to this next thing. Okay, so what we are going to do today is to look at the pair difference. Okay, so let's recall why we need pair difference. And the data of the pair difference is now is not in the independent population, is related. Okay, so you can imagine that as very often people would set is the drug or treatment. Okay, so you may want to see some people, right, look at, say, how maybe you are testing cosmetics. Okay, so you are saying, CO, look at the cosmetic, look at your skin, how yellow, or no, don't you suppose you want whitening. Okay, then you want to see, I'll put there, and after 3 months, is it white more or not, right? Or you want to use sunscreen, sorry, sun cream, then you want to say, oh, there is a sun cream going to protect you from the sunshine. Okay, so this is usually before, right? And then you have an after, right? And then you have to pair the two, right? Because usually this is how you avoid the individual difference, right? You compare this, right? Look at difference. Is it going to make a difference, right? Or some people are saying that, oh, eating that certain drug can make you slim, right? The difference, and make you taller, and so on and so forth, right? Um, that's the difference, and this is often used in many experiment or on the policy, right? Say now the Hong Kong government was giving some money to employer to keep employment, right? 保就业, okay? Then you want to see after the government give money, is it going to fire people or not, right? And clearly doesn't apply for Cathay Pacific, right? They get the money and then after a while they still fire people. There, I mean, those kind of issue. But anyway, policy is a very important application for this because this is what you do. And then obviously you can see this is a very standard thing you see in science. So that's why this is the basic thing. When you do a science, you go to the lab experiment, this is the very standard thing you do. Okay. So what you hypothesize is, okay, there's a two different group, 1 and 2. Okay, usually it's a before after the standard thing, and then you usually hypothesize the difference is equal to some difference, and it is usually 0. Okay, but sometimes you can say there is some difference because you know the difference. You can say there's some difference, but most likely that would be 0. But when you have non-zero, maybe I think you know the sun cream, they have SPF 35 and SPF 50, then you know they must have a 15 difference in terms of SPF, right? So for those cases, then you know. Okay. And the alternative is same, is just not equal. Okay. And the pair difference, okay, for each observation, okay, this is called as x1 sample, this x2, right? The first element is x1, 1, the second one is x1. So observation here, it will be x1, 1, x1, 2, x1 n, okay? And the observation for this one will be x2, 1, x2, 2, x2n, and do notice a pair observation. So we assume that for each observation we have the same sample from the two population. Okay, we observe the say We also have another one, okay, and they're linked. You can imagine they come from the same subject, okay, the same target you're targeting, but you're just observing a different time before and after, okay. And what you do is you have this sample. Instead of using them the same, you take a difference. So each one take a difference, okay. Doesn't matter who subtract from what, but it's just consistent. Here I use the term because the now is 1 minus 2, so I take the before minus after. But you can reverse it, doesn't really matter, okay, to the difference. And the mean will be the average, the sample mean will be the average of those, okay. And because they are normal and the difference, right? So if you know, we don't know that sigma, okay, suppose they may have the same or different sigma square, right? We don't really know, okay, but we can estimate the so they may have sigma 2 square, and this guy may have sigma 1 square, okay, and they may be related, right? So this the standard deviation from that from the x1 minus x2 can be very complicated, okay. We don't really know. So what I mean is this d, okay, with a normal distribution, okay, d bar, all right, function of a, okay, this is the mu d, okay, and this is sigma d hat square. The d bar square is not easily known unless you make some assumption here, right? But we can proxy by the sample variance, okay? This SD. You can do this to the sample counterpart, and you replace T, then you're done, right? If you don't assume any structure, then you will be using the T1. Okay. And do note that because we have T observation, so your standard is a T n minus 1, degree of freedom is n minus 1. So it's not n minus 2. Although we have 2 samples, it doesn't imply we minus 2 because we still have T, we still have n observation here, okay? So this is the, right, because you can easily show, right, this is normal CO1, right? And this is still a chi-square degree of n over n of square root. So this is still a TAN minus 1. Okay? Because we don't know how they're related, right? So that's why we use the sample version. That would be much easier to do. If you know, then we need to know how they're related, then we can write a z test, but here we can't. Or we make some assumption on the, okay? And next slide, if no question. So let's so here we have a SD, right? The standard error, standard deviation is equal to the mean over n minus 1. So this is a sample one. Okay. The critical value will be the same. Again, do notice n minus 1. Okay. And this is no different from the X bar thing, right? It's the same thing. Right. This is the S, right? So the same thing, but you just treat the difference, follow a normal distribution, right? One way to assume is the difference will follow a mean. So that's why that would be the proof. But let's see the example. Okay. So now we're medicine test, right? We have a control group and a treatment group. Okay. Control group, basically you gave them the placebo, right? And the treatment you actually give drug, right? And then you randomize over them, right? You don't know if you're a doctor and the patient doesn't know, they don't know who is given what, right? So you say double-blind experiment, right? And here with sample 16, and the sample mean is difference is 1, and the SD is 2. Okay, so we're trying to see if this is equal or they're not equal, right? If they're equal, that means the drug is not useful. Okay. If useful, then the drug can be useful. Okay. So I guess there's a typo here. This would be because I put it 0, so this would be 0. Sorry for a typo here. Because this would be mu1 minus mu2. Okay, this is 0. So this is D, okay, D bar. And this is 2 over root of n, right? So this would be 2 rather than, sorry, the mistake. Okay. So it's okay, still 2, so it doesn't really matter. So basically, again, to repeat, what I have here is we have D bar, okay? According to the null, this should be 0, right? And this is normal, but we don't know this, I don't know, okay? But that's why we use T, n minus 1, okay? Which is T15, okay? And the data we have actually is like here, 1, right? So we want to see they are two-sided, right? So we want to check whether the two-side area, right, the symmetric one, -1, okay? This symmetry here is bigger than alpha or smaller than alpha, which is 5%. So it's two-sided, right? So it's alpha 2, okay? Because you want to check this and this is bigger than alpha 2 or less than alpha 2, okay? So you basically convert this one into the Z space, right? Maybe I use other color. Okay, this again is 0 here, and you convert to the T space. This one is become 2, okay? And you want to check this area, okay? Or you want to see the critical value, right? So let's do the first thing, check the area first, okay? You check this area, how you check this, right? This is T inward, sorry, T distribution, okay? And then you have a 2, degree of freedom 15, true, okay? And because you look at the double of the area, you double the area compared with alpha, okay? And this area is left-hand side, so 1 minus this guy, okay? And you have to multiply by 2, okay? And then you compare with the alpha, and then actually bigger than alpha, 5% we use. If 5% is not going to reject, okay? So if you 5% alpha, then it's not, you cannot say the drug is useful. If you use 10%, then the drug will be useful, but 5% not, 1% not, okay? And alternatively, you can look at the two-side one, right? You want to look at what gives you 5%, right? So alternatively, you want to look at the other cases. You want to look at this both side, right? Is equal to alpha 2, alpha 2. What is this number, right? This number is T15 negative. 0.025. Okay, so for the XL, it will be T dot inward. Okay, 0.025. Okay, and then d equals to 15 will give you the negative 2.13, which is this answer. Okay, and look at the absolute value. It's more than 2, so it's more extreme than 2, so you can't reject. Okay, so more or less we have is you cannot say the drug is useful. Okay, so just to remember, this is a very common way when you have a test of drugs. Okay, any question? If no, then let's continue because we start a bit late, so we cut short a little bit the break. I'm sorry. So here we have technical proof. Okay, so what we said is the difference follow the mean, so that's why everything follows one sample test. So that's a proof behind. So we are not going to consider further. Okay, so that is proof. We're one line proof. So let's finish this one. We have a break. Okay. So we have a z test for proportional. Okay. So there's no different from what we have before, but we have some technical difference. Okay. Just saying the difference in mean, right? It's no different from x bar 1 minus x bar 2 is equal to some number a. Okay. And you will also see the only difference is we will use the normal, okay? Because we can estimate the sample variance, okay? This is the, if you recall, right? This is, if they're the same, right? If they're the same, so let's focus on the case where that A is 0. Okay, but A is 0. So focus on, let's make it easier. Let's forget about A, let's make it that 0. Whether equal or not equal, that may be even easier. Let's focus on this case. There's 0, okay? And that the sample proportion are the same, okay? That means under the null, right, pi 1, sorry, P1, you have a normal distribution of pi 1 minus pi n 1, okay? And P2 will be n pi 1 minus pi n2, okay? So pi is what they're equal to, right? P1 with pi 1 and pi 2, but they're the same. So that's why under the null hypothesis, they're the same pi, okay? And that means that their difference, P1 minus P2, okay, will follow a normal distribution, right, with pi, and that will be pi 1 minus pi n1 plus pi 1 minus pi n2, because they're independent sample, okay? So that's why under the null, right, you know the sample mean, right, which is P1 and P2, right? So that's why you can rewrite this as a normal, right? That's why P1 minus P2, okay, minus pi 1 minus pi 2, okay, will be equal to this pi n1 n2, okay, you take this out, give you this answer, and pi is replaced by this pi bar, which is the sample proportion, okay, the common sample proportion, which is pi, or this will estimate this guy, okay, what's this guy? It's x1 plus x2 over n1 plus n2. Okay, so looks a little bit tricky for the variance, okay? Sorry, for the sample proportion, variance sample proportion. The idea is like this. Okay, why you want to test this is go back to the original thing is why you want to do this, right? So usually what you do is you may care, suppose the two group of maybe why you this kind of question, right? Go back to the question is suppose you have a bunch of consumer from Hong Kong Island and other from Kowloon, right? And then you would focus on whether maybe see proportion of people like spicy food, right? And then you see whether they like spicy or not. And then here I also look at whether they like the spicy or not, right? And then you want to see they're different or not, right? If they're the same, then you can use the same menu if you're a restaurant, right? So on and so forth. This kind of question you're asking, whether they're the same or not, right? If the same, they can treat the same, then you can use the same business strategy, right? So this is the reason why we have this kind of question. Or you want to check whether, say, the election, you want to see this support for Trump is the same, or support Biden the same across different states or not, right? Are they the same support from women, same support from the black, same support for the brown, same support from the right, from the white? So that's why that's what you are testing. So here is you take the difference of the sample minus what you propose, usually zero, right? And this is this using this total, you just because they're same, right? So that's why you add them up. It's the best estimate of the pi. Okay, you replace it, then this will become a normal. Okay, so that is one interesting technique used here. Okay, so the only complicated part is just to recall this part only, right? Because this is the sample proportion, and this is the when you have proportion, this is also the best estimate for the variance of the underlying population, okay, which is given by you can see the next slide will be x1 plus x2 over n1 plus n2, right? Just like the total spicy customer would like spicy food over the total sample you sample from the Hong Kong Island, Kowloon. Okay, so that is the only tricky part here. Okay, so very quickly, as we have said, and this is the two-tailed critical value, and here is the most tricky part here. The most tricky part here is now we have some difference between the interval estimation and hypothesis testing. Okay, here is not, we are not using p bar 1 minus p bar and 1 over n1 over n2, right? We're not using this. Okay, we're not using this. Okay, the reason why we can use this, okay, is because this is true under the null hypothesis. Under null, that's true, right? Under null, there's single p or single pi, okay, because p1 is a normal with pi 1 minus pi over n, okay? And P2 is also have a same, okay, the same mean, okay, which have the same variance, okay? So this is coming from assumption of the same mean and hence the same variance. But here the confidence interval estimator, we don't make such assumption, okay? So that's why we have to use, we will well have this, right? Instead we have P1, right? We'll have the normal pi 1, pi 1, 1 minus pi 1, and over n1, okay? So you estimate pi 1 by p1, right? And the same goes the rest, right? So that means that we no longer have this assumption, so that's why we cannot combine, okay? And what does that mean? Actually, this is bigger than this one. So this is A, B, you will figure out that A is bigger than P. Okay? Can you see the proof this is the case? Because P and 1 minus P is the mean of that. So that's why we don't have this, then the interval estimator, the width will be larger. Okay? If no further question, then let me continue to the example, then with a break. Okay? So the two population, okay, random size, sample size n1 is 50, okay, and sample proportion is 0.6, so P1 is 0.6, and n2 is 40, and sample proportion on that case P2 is 0.7, okay? So we are testing whether they're same or they're different, okay? It's a two-tailed test. And the first is to calculate the pooled proportion, okay? And here x1, okay, is how many of them is 30, because x1 is p1 times n1. So x2 is 28, okay? So you can use the formula we have here. It's just x1 plus x2 over n1 plus n2, right? So it's just 30 plus 28 over 50 plus 40. So it's 58 over 90. Is that okay for the pool proportion? Okay. And if that's okay, then we continue, I guess. So this here, just apply the formula. But again, let's before we do it, let's draw again what we are working on. So we use the same standard graph. We draw again, right? We're looking at P1 minus P2, right? That under the null, they're the same, okay? And the variance actually we know, right? We say they are the same proportion, then that's actually they're equal to some number, right? Let's call pi, right? Would be pi 1 minus pi over n. Depends on how many sample you are drawing. So suppose you draw n1, n2, so it will be pi, and that would be 1 over n1 plus 1 over n2. Okay, so that would be the. And since we know this, then we can convert, it's a normal, right? Then we can convert, normalize it to the Z space. Okay. And you can see one is 0.6, one is 0.7, and one and two is negative 0.1. So it's somewhere here. So again, you want to check two-sided one. So the symmetric case, point one, is this 2 bigger than alpha, or look at, is it alpha or 2? Okay, it's bigger than or smaller than. Okay, so that's the key here. And then we need to convert them to the z space, right? So that is the goal of the next slide, is to try to see if negative 0.1 is equal to what? Okay, this is 0 again, and this is what's this number, right? How to convert it, right? You just this negative 0.1 and divided by this thing, right? Will be the p bar, 1 minus p bar, and 1 over 50 plus 1 over 40. Okay, so that is, this will be a normal CO1, right? So that is what we have in the formula. Okay, so figure out that this is the P 1 minus P, okay? Because this from the last slide is 58 over 90, okay? And input the data, you figure out that this is, look at the Z, okay? From negative 0.1, okay? You convert to Z, negative 6.234. So it's so large, right? And actually, you don't even need to work out the answer, but you can check this number. What's probability of this one, right? You use the p-value. It's a typo here, so there's 2 times. Okay, and you check this one will be effectively 0. Okay, so 2 times 0 is again 0. Okay, so that's why less than 5%. Okay, and of course you can check 0.25. Not going to do it. It's 1.96. Okay, that's why that's the case. And do note that we cannot just plug in this number to here, right? We will be doing this directly. Apply the formula P1 minus P2 plus minus C alpha over 2, okay? And this will be P1 minus P1 over N1 plus P2 1 minus P2 over N2, okay? So that would be the case. Okay. I think that should be, we should have a break here. Let's have a break of 5 minutes. We're shorter break because of the time. So let's resume at 9:40. In the meantime, I answer any question that you might have. It's a break. So I guess we should resume. So any question about the thing we covered before the break? If no, then we continue. Just repeat what we have just said. So why we would have that particular formula is because for confidence interval, calculate the variance of this, right? And we will be looking at the variance of this will be estimated by this guy. Okay. And under the null hypothesis testing, they're the same. So that's why we estimate for this way. So that's why with this formula, this is smaller. Okay. And let us, there's no problem. Let's cover the final thing. And I think we have some time, then we'll go over the Excel. Okay. So no further question, then we talk about the last object of this topic is compare variance. Okay. So basically you're trying to see if not the mean now, we want to look at the variance. Are they the same? Okay. So look at two sample. Okay. And they have the same mu1, mu2 square. Are they the same or different, right? If they actually, why do you want to do this? If you want to see if this is true, then you can apply the t-test of the same variance, right? So that is, you want to support what you're doing, right? If this is right, then this is a good support for what you just said, okay? So how to do it? Turn out to be rather simple. We prove it soon. The proof is very simple too. So it's just very simple. We look at the ratio of them. Okay. You can compare, you can do S1 square over S2 square, or you can S2 square over S1 square. Look at the ratio. Okay. You want to see where the same, compare the ratio. Okay. And obviously the idea is if they're equal, they should be close to 1, right? I mean, if the same, it's close to 1, right? If the same, okay? So the main idea is look at the following. So we're looking at S1 square over S2 square, right? Should be somewhere 1, not 0, it's 1 because they're same, okay? You may ask why we don't do the difference, okay? Turn out to be this one is not easy to do, but this one is rather easy to do because this one turn out to be a chi-square, right? Because the sample variance is chi-square over chi-square. Chi-square over chi-square is f, okay? So turn out to be this is, depends on the shape, depend on how many sample you have here, somewhat like this, okay? This is from 0, okay? Something like this, or sometimes it's like that, okay? It's not symmetric, okay? Can be anything, okay? If you recall what we learned last class, okay? And so that's why when you calculate critical values, okay, it's not symmetric. So you have a left hand and your right hand side. Okay, we'll talk about that in the Excel spreadsheet very soon. But turn out to be careful because not symmetric. So you try to look at, they're not the same, so look at two-sided. So you would be look at alpha 2 on this side, alpha 2 on the other side. And this is not symmetric. Above again 1, so this is not symmetric. So you have to be careful. You have to look at this alpha over 2 and 1 minus alpha over 2. They're different. Okay, so that would be some key here. So let's clean that up. Okay, so we can look at this, the right tail, 5% give you this number. Okay, and the next example will show you how to get these numbers out. Okay, so for F, you can still do p-value, but usually we do the critical value because it's asymmetric. That would be easier to do. Okay, you can also do it, but the standard way is look at the okay, so constant two population, sample size, sample of N1, okay. So N1 is 50, okay, and sample variance is 30. So S1 square is 30, okay. N2 is 40, so sample variance is 20. Okay, so that is the what is given from this question. And you want to see whether they're the same population variance or not. Okay, the same or they're not. Okay, so again, what we have said is you look at the ratio. Okay, F will follow S1 square, S2 square. Okay, and this is 1.5. Okay, and this should be F. N minus 1 is 49. Sorry. Oh, so there's a typo here. So 49. 39. I guess I mistaken this. So let's see what other answer. I think this is a typo. Okay, so this is 49, 29. Okay, and you should look at this F values. Okay, so let's see how we are going to do that. Okay, so look at the Excel. Let's open Excel. Guess I can share the screen one. So here, let me zoom in. Okay, just to recall, we have a typo here. We are going to look at 49 and 39. So let's show you the. So the N1 is 49, N2, sorry, 40, 50, okay? And we're looking at 0.025 and 0.0975, okay? So that's what we do. We're doing the F because we find a critical value, so we are looking at the F inverse, okay? There will be left and the right. So inward, look at the left, okay? Left-tailed, okay? Probability with 0.025, okay? And degree of freedom will be 49, 39, okay? So this is the formula here. Okay, so it should be, okay, so this number, if it's 49, 29, then the number is 0.5530, okay? And Next, we want to look at this, the right tail, 0.925. Okay. And look at that. So there are two ways to do it. You can use f dot inward and 0.975 and 49, 39. Definitely can do that. Okay. Or the other way around, you can use what we call f inward dot right tail. Can look at 0.025, 49, 39. Okay, give the same answer. So this right tail will exactly give you the right tail. So it's 1.8. So if you trying to write down in this number, should be 1.84. So still this is true, 49, 39. So this is still true, and we do not reject. Is that okay? I hope you can see the Excel. Is that okay? I hope you, because this is the last one, last example we're doing. So let me know if you have a question. If you're okay, can you type okay? So the two critical value, two side 5%, 2.5%, and then it's within, they don't reject, right? It's outside, they reject. So that is the thing we use. Okay, I can explain that graph. So the idea is, so let me draw it out. So here is, we have S1 square over S2 square, right? Supposedly, if everything is right, it should be 1, okay? But it's not symmetric, so it depends on this. So something like some shape like that. Something like this shape. And do note that this is coming from 0, right? Can I go beyond 0? It will be 0 to infinity, okay? Is that okay? Hanu, for this up to here. And now we have is, look at the alpha is 5%, okay? So which means that I apply, here is 0.025, and here is 0.025, okay? And how do you find this? Either the two way to do it, right, is f inward 0.025, or 0.975, okay? And you put the degree of freedom, which is 49, 19, right? And or you can have inward right tail, right? 0.025, 49, sorry, 39, okay? Which is give you the 1.8, okay? And here you have f dot inward 0.025, 49, 39, okay? And this number is 0.55, and what you get is little bit, the data you have is 1.5, right? So it's here. Okay, and it's not in the rejection region, so that's why you are not rejecting. If you beyond 1.4 or smaller than 0.5, then you reject. Is it okay? Is that clear now? So even though you can see they look different, right? Seems like big enough difference, but the sample you have is not enough to say anything, right? If you do more sample, then you will see this is going to be fine. But you're not having enough, so that's why you were not rejecting. Okay, and let us go back to the slide if you don't have any question. Any more question? Because that's the case, we'll finish the thing and then we will finish the slide and then we'll talk about Excel. Okay, try to see if something we can set about Excel. Okay. Here, just try to convince you that actually the what are we going to do in the last slide? Of course, it's technical slide. I mean, you can see the technical slide. It's trying to show you why this S1 over S2 under this null, that the same variant will give you the F. Okay, this under this. Okay, the reason is this over this, right, can be rewritten as here we have this, right? Can okay, let's write that down. S1 square, right, will be summation square over N1, right? S2 square will be, let me write that down maybe, right? Summation x2 I minus bar x2 bar square over N2 minus 1. Okay. Okay. And you take a division, right? We will have you all this term here. Okay. But the numerator denominator, you just multiply. You can multiply and dy. The same guy. Oh, sorry, not the same. You divide this here, you also divide this here. Okay. I think I should be writing more properly. I think this should be 1. This should be 2. Yeah, I think that's typo. Sorry. This should be 1. And this should be 2. Because you divide and you multiply again. Yes, so this is 1, this is 2. Sorry. And okay. And do note that this first element, right, is a chi-square distribution of N1. This is also chi-square. This is also chi-square N2 minus 1. This is chi-square N1 minus, sorry, this N1 minus 1. Okay. So, and so that's why you replace this is, you replace, okay, this guy is chi-square minus 1, so we place here. And this guy is here. Under the null, they're the same, so we cancel out. That's why you have N1 minus 1 over N1, right? This is exactly what the F is. So definition. Okay. So that's the proof, but I guess most of you are not interested in the proof. So that's why we are going to talk about Excel. If any question on the overall, because next class we have a quiz on this set of slides. Okay, just to probably I should put that on is about the project and also the test. The test again. Let me repeat. The test will be on the as you see in the syllabus, will be on the November 26th. Okay, I'll put that announcement on the blackboard again. Okay, 26. Put that on. Okay, if there's no further question, then we'll go to talk about exam Excel. So just I'll give you one minute to think about whether you have question or not. If no, then we are going to talk about the Excel. Maybe it's good to look at the slides if you have anything to cover over there, Excel. So, okay, so I think there's a several things we can cover. Okay, so I guess we can cover several things. Okay, so let's see the slides. Okay, so I think I look at the Excel slides. There are many. I mean, actually we cover a lot. Okay, so I guess I want to cover the first thing is the estimation part, where you have a confidence interval. Okay, I think that would be the first thing we want to say. Okay, so here is the how to estimate the confidence interval, and basically this Excel function called confidence norm gives you margin of error. Okay, this is basically what this is give you the margin of error, right? And the confidence interval normal will give you this guy, right? Sigma over root n. Okay, so basically this you would input the alpha, which is here. Okay, and you put sigma is here, you put n. Okay, you have this function directly give you the answer. Okay, so basically this is just you have this is just norm, right, as inward, right, alpha true, right, and this is what it is, right? So that is the standard thing, right? So this is how the this function looks like. Okay, so see the example. So if you have mean x bar, right, this is x bar, okay, and this is sample size n, okay, and you know the sigma, and you know your confidence, which is 5%, right? Then this will give you the two-tail by saying C2, okay, which is the alpha. Yes, this is only the norm is the normal. We'll talk about the confidence T will be the sample, yes. This is the norm, you know this is sigma, we know it, then you put in here, and then at the end you have C4, which is n, okay? Just remember this is the alpha sigma n, okay? So this gives you, this is actually the marginal error, okay? Confidence norm, okay? Of course, here we show you, you can directly do the calculation, right? You can do the 1.96 divided by, look at the C2 0.025, standard normal, and then calculate this guy, and then you multiply the same thing, right? Multiply by using this z alpha 2 times the sigma, okay, which is C1, right, over the root n, which is C4, okay? So this is what it is. This is the marginal error for normal, okay? I don't think I need to go further on this because they just save some calculation. I don't think this function will be, we don't need to divide alpha by 2, yeah. Oh, here is two-sided already. So here ME is two-sided. That's not, yeah, you don't. So it's, yeah, it's very fun. Yeah, you don't have, yeah. Because they automatically assume two-sided and you put alpha. So the input is alpha. So the question is very good. Is alpha here? But when calculate alpha by 2. So, so the next part, of course, this is not very useful because I think this doesn't save you a lot of time. And the next one, I think this one is T. I think it's more useful, right? This one, this calculate marginal error again, right? It's T n minus 1 alpha over 2, right? And this will give you the S over root n, okay? If you have, when you have this data, right? Because this depends on your alpha and actually your sigma actually is S, right? It's alpha sigma n, okay? So the same thing here. Is that okay? This is the idea, but you can see the example, then you will see this is the same thing. So this is confidence T, give you the 1 minus alpha confidence. So it's two-sided again, okay? Because this is a confidence interval, right? So it's not, there's no one side, it's always two-sided. Okay, so let's see the example. To save time, I'm not going to run it in the Excel. You can check it. So this is the alpha is this. So this is data here. Okay, I calculate the mean, right? It's average. Okay, I look at how many of them. I use the count function. Okay, and the standard deviation. Okay, to SD dot S. Okay, so standard deviation. So calculate marginal error. So marginal error, you just remember, it's just put in alpha, S, and N, right? So that's why it will be alpha, S, and N. So it's C1, C4, C3. Okay. That's alpha, S, N. Okay, so that's how we do it. Alternatively, you can use two-sided, two-tailed. You can use this one. We didn't talk about this, but this is same as you do T dot inward, because alpha is 0.5. Okay, you can use 0.9, sorry, 0.975. Okay, degree of freedom is 5. Okay, and this will give you the same answer here. Okay, you can use two-tail. When you do two-tail, then you can just put alpha. Okay, if you have one tail, then you have to divide by 2 in your mind. Is that okay? Because this is the two-tail thing. Okay, here again, you can use your own calculation to do it, or you can use the confidence dot T. Is that clear what the confidence T and confidence norm are? So we learned two things. It's just to construct the confidence interval. Is that okay? If there are no further question, then we continue because I guess that would be hypothetic. Okay, so this is something we learn the whole whole part, so C test, and also the T1. I think the T1, okay, let's go on. Let's see what we have in our slide. So we had one sample and two sample. One sample you Z, you don't have the T here. And for the two sample, you have the T test, F test, but not for the Z. But Z is, you can just follow the one sample, right? Because they're same. Okay, CH and use C test. Okay. So let's forget about this. Let's directly go to the question. Okay. You are using the right tail. Actually, you can use the C doc tags to calculate what we want to do. Okay. So let's see from the Excel. Okay. So this is data. Okay. And for the C test, this is the mu is coming from the, we know the mu, we know the sigma already. This is the variance, or the variance is 4. Okay, so this is the population variance. Okay, and the mu is 4. It's come from H null, right? So you want to see whether mu is equal to 4, right? X1 is mu not equal to 4, right? And the sample size is 6, so this is counting from A2 to A7. Okay. And the mean will be average out, so just average of those. So 2 plus 2 plus 2 plus 3 plus 3 plus 4 plus 6 divided by 6. Okay. So now remember how we do the z-test on the right tail, right? So you calculate this x bar minus mu over sigma over root n, right? And this number, we calculate the right tail, right? So this is the z here, right? And then right tail, we're trying to see what is this area, right? So basically is you want to see the 1 minus this inverse, right? So basically just 1 minus the probability that z is less than that guy. Okay. So one thing you can do, right, is to directly do the calculation, right? Let's see whether we get it, right? So it just, I think there's a typo here, should be C4. Okay, would be the mean. So it should be 3.333 minus 4, right? Over sigma, which is 2, over the root of 6. Okay, so that is what here is. Let's be 3 here. Sorry for a typo here, I guess. I forget to copy and paste. I mean, the answer is right, there's no problem. And once you calculate, this is negative 0.816, right? And then you do 1 minus normal because this gives the left-hand tail, then you do this, okay? And it seems like doing this is rather complicated, right? You may imagine. So that is a good thing is these z-tags can directly give you the answer, okay? So here the tags, where actually you look at this is we directly plug in the data. So the data here, you plug in the z-tags, you put in data, which is A2 to the A7, okay? And then you tell them what is, I think this is sample size. No, this will be C2. This will be 2, sorry. This is 2. And you give them the variance 1. Okay, so that's give you the z-test directly. Okay, so your data, if you give an data, then you can skip these 2 steps, directly go to the p-value. Okay. Is there any question? Or you want me to do it on Excel? Or is it okay? Is that okay? Okay. So, and the left tail they don't have, they just 1 minus because the p-value on the left side and right hand side. So you just do 1 minus. That makes x mu sigma. Okay. And the left tail, same thing, just 1 minus. So it's just the left side. So it's just 1 minus this guy. So I'm not going to repeat this one. And for the two-tailed, I don't want to talk about this. For the two-tailed, the definition of two-tailed is the two-tailed p-value is this is z. Okay, you look at the left-hand side, okay, or the left-hand side, okay, and take the minimum. Okay, why? Because this is symmetric about 0, right? If you're on the right, you take the smaller one, the right-hand side. If you're on the left, either you have this side, right, or you have this other side. Okay, that's why the minimum of the left and the right. So it's 2 times minimum of the left tail or the right tail. Is that okay for this one? So I think you know how to do Excel. I think I'll quickly go over the last one because people asked me the question about the T, right? So I quickly, so this is the way you do the two-tail. So I think I want to talk about the t-test, okay? The t-test quickly is, again, there's no built-in for the simple t-test, so you do from the scratch. So there's nothing to talk about this, you just do it from scratch, okay? So just, there's no function, you have to rely on the statistics, okay? So that's no, you cannot, like this, you can have a data, automatically calculate. So you have to start from the scratch, calculate the mean, sample mean, standard deviation, calculate t, calculate n, and look at the t distribution. So there's nothing is different from what you have from the slide except the last step, right? The same thing. I mean, there's nothing deep here. So I'm not going to talk about that. I think we have already covered this part. So the sample proportion is the same. I think there's nothing new here. So what is new is this guy, okay? So t-text. So t-text, you input 2 data set, okay? And tell them what kind of tail is right tail or left tail. So I think that's right tail or two tail, okay? The left tail will be 1 minus, right? Because this is the p-value. And the key here is someone asked me whether we have a shortcut to the calculation. Yes. We have either you have paired, which is the difference, right? And equal variance or unequal. So that's exactly coincide what we learned in the class. Okay. So let's see quickly. I guess I overrun a little bit. I know. I quickly done. Okay. So pair is simple. We have x and y. Okay. Of course, according to the book, you go to the data, take a difference, right? And calculate the mean of this thing, calculate SC of this guy, right? Standard error, right? Over the root n, and then calculate t, and then get degree of freedom, and give you the p, right? So you can go all the way down but you can do directly. Give you data t-test, give the data. I'm doing a two data A2, B2, right? This is X and Y. And you give him white tail or whatever here, or the right tail test, or if you want two tail, you give two. And you also tell them what kind of doing. You're doing pair. This one, this is pair. Okay. So then you get the same answer. Okay. So that is shortcut. If you're looking at data, then you have shortcut. But if you don't have data, there's no fast way. So if the data start from data, you can forget about all this, right? You can just forget about all this. Okay, directly go to the answer, the p-value. Okay, and similarly, you have the same when you talk about the t-test. Okay, you can do the same, right? You can equal variance. Okay, you can have the x and y. You can do all the calculation as we do in the slides, but you can directly go to the answer. Give us the x, give us the y, say one tail or two tail. The second one is equal variance. Okay, so again, we have covered this in the class already, but we're telling you give two tests, you can directly tell you what's the answer. Okay, do note that I use right tail, but most of the time you use two tails, so you can use two in the most of the case. The same goes on for the unequal. Okay, unequal, we get the same answer. You have the same x and y. You can do all the calculation, right? And the most difficult part is to calculate the v, right? I think this is the most thing you would want to avoid this formula, right? Then use the t-test, use the third style. Okay, I guess I should end here. Don't worry about the Excel again, because unlikely you will have any use for your quiz, because it will be useful for your assignment, but not useful for your quiz, because the quiz will just give you the like what the example you see in the slides, and then we go over a little bit more about the Excel after the quiz. But just very quickly, we go over this. We go over again for the Excel, so don't worry. I just want to talk about this because you want to know more. But anyway, have a nice day, and then we'll have a quiz next class. Okay, bye-bye. Thank you. I stay around to answer the question you might have. Thank you. Bye-bye.